Hi everybody, welcome to the next presentation from Milad Abolhasani. He is an associate professor at the North Carolina State University, and today he will tell us about the rise of self-driving labs in chemical and material science. Milad, with that, over to you.
Great. Thank you, Christopher, for the introduction. I want to start by thanking the organizers for the opportunity and kind invitation to present some of the recent work in my lab on modernizing materials discovery and manufacturing through convergence of flow reactor engineering, robotics, and data science to build the self-driving labs. So the main question that we're trying to address in my lab is how can we accelerate the discovery and development of advanced functional materials from years down to months or even few weeks. So to answer this question, first we need to know the current major challenges of materials discovery and development. So the first one is the time gap between experimentation, running an experiment, and making a decision about the next experiment that you want to test. Second one is the scale gap between the lab scale, bench scale discovery and large scale manufacturing. And the next challenge is the heat and mass transfer limitations and the batch-to-batch variation of the current batch reactors that is a gold standard in academia and industry to synthesize advanced functional materials. And the last one is the disjointed workflow between upstream material formulation synthesis and downstream performance evaluation. So these two are typically disjointed, multiple different groups of working on upstream and downstream of materials development workflow. Now, because of these challenges, when we're looking for a new material within this chemical universe of infinite and intrinsic and extrinsic parameters, we end up with a labor, time, and resource intensive material exploration because we don't have a map of this universe. So most of the time that we are looking for a new material, we're blindly searching through this chemical universe. So in my group, to address this time and scale gap problems that I mentioned in the previous slide, we're working on this concept of universal self-driving lab through integration of a new type of reactors to run reactions in a miniaturized fashion. These are called flow reactors. With robotics and online characterization tools in a highly modular manner, and have the whole end-to-end experimental workflow operated and guided by a modular AI modeling and decision making strategy to guide our navigation through this infinite chemical universe. So this self-driving lab acts like like an intelligent robotic assistant for human scientists to accelerate the discovery and development of advanced functional materials. What I want to highlight here is the modularity of this self-driving lab that would make this search through this infinite chemical universe completely hands-free without any user intervention. You can have this closed loop operation of navigation through that chemical universe based on the objective functions defined by human scientists. Again, what I want to highlight here, this is not going to replace human scientists. This is like an intelligent assistant for operator or scientists to accelerate R&D to save time and cost of discovery of new materials or new synthetic routes. So as the heart of this self-driving lab in my group, instead of using batch reactors to synthesize materials, we use what we call flow reactors, which is basically the field of flow chemistry, running reactions in tubes or microchannels, and materials are being synthesized as they're flowing in a tube or again a microchannel. Some of you might have heard of the field microfluidics. So all these reactors are coming from the field of microfluidics. So some of the reasons that why we choose flow instead of batch. The first one is the enhanced and reproducible heat and mass transfer rates that you get when you reduce your characteristic length scales of your reactors from tens of centimeters to a few hundred microns. The second one is the reduced chemical consumption from hundreds of milliliters of batch reactors down to a few hundreds of nanoliters or few microliters per reaction condition when you're searching